Welcome back, everybody. This is the Radio Signals podcast, and my name is Mark, and my call sign is N9WIB. This is the Technician License Series, and today we will be presenting Lecture 4, Electricity Fundamentals. During the presentation, we're going to review the concept of electricity, define voltage, current, as well as introduce very basic circuits, and then also introduce some very basic test equipment that's used in the analysis of circuits. So what is electricity? Electricity is essentially the flow of electric charge. So what carries that electric charge? So the electron carries that electric charge, and an electron is a subatomic particle. What does that mean? It means that an electron is a component of an atom. And other components of an atom include protons, neutrons, and of course the electron. The proton and neutrons comprise the center of the atom, while the electrons orbit on the outer side of the electron in what are called shells. So the electrons have a negative charge. The protons within the center of the atom have a positive charge. And neutrons, which also make up a component of the center of the atom, have neutral charge. So again, the atom is composed of protons, neutrons, and electrons orbit the outer shell, and the electrons essentially carry a negative charge. A unit of charge can be defined as the coulomb. So the coulomb is depicted in SI units as a capital C. And the charge in coulombs on one electron is 1.6 times 10 to the minus 19th coulombs. So said in a different way, it takes a lot of electrons to make up the charge for 1 coulomb. So 1 coulomb of charge is equal to 6.24 times 10 to the 18th electrons. That's a heck of a lot of electrons. One of the core properties of electricity is that it is composed of current. Electricity must flow to be useful. That flow of charge is called current. And the flow of charge can be also known as the flow of electrons, since electrons carry a charge. So flow is defined as the passage of some type of physical object or electrons over time. The unit of charge is defined as the coulomb. So therefore, current is defined as the flow in coulombs per second. 1 amp equals 1 coulomb per second. So you can see that 1 amp is equal to 6.24 times 10 to the 18th electrons flowing past you every single second. So that's a lot of electrons. If you want to use another example, you can see that 6 billion superfast alien cows are zipping past you every second for the equivalent of 1 amp. That's a lot of cattle. Another common analogy used to define current is that of the flow of water. So a very slow river can be defined as slow or low current. A very fast-moving river, or a lot of water flowing over a short period of time, can be considered a very high or fast current. Conventionally, current is thought to flow from positive to negative. This was established by Ben Franklin with his experiments in electricity. However, Ben Franklin got it wrong. Unfortunately, we kind of use this concept to the date today. In reality, current flows from a surplus of electrons to an area that is in need of electrons. It flows, in actuality, from negative to positive. But conventionally, we use the flow of current from positive to negative, thanks to Ben Franklin. So, go back to the old days. This is the way we typically use or depict the flow of current from positive to negative. And stick with the conventional definition, but appreciate what reality really is. Voltage is another component of electricity. It's analogous to pressure, as current is analogous to the flow of water. It is the difference in potential electrical energy referenced between 2 points, and typically in electronics is going to be referenced to ground. It can be expressed as volts or electromotive force, known as EMF. EMF is abbreviated E, and volts has the abbreviation of V. Another way of expressing voltage is energy per unit charge. So that could be joules per coulomb. A joule is equal to the amount of energy it takes to lift a typical apple 1 meter off the ground. And that's a practical example. And a joule is a unit of energy. So 1 volt will equal 1 joule of energy required to move 1 coulomb of charge through a component of an electrical circuit. So we can use more practical depictions. Let's think of Hoover Dam. So being upstream and downstream from Hoover Dam, as you can see in this picture, there's a significant amount of water and there's lots of potential energy. So all that energy is stored behind the dam. If the dam were to fail, all that energy and water pressure would be released. So this is equivalent to high voltage. And when we discuss the Hoover Dam, that's literally with the hydroelectric energy that's being produced by the dam. And if we think of a glass of water, this could be analogous to low voltage. Not a lot of potential energy. If the reference point is the water inside the glass compared to the outside of the glass, if the water spills or the glass breaks, not a lot of energy is dissipated. So a minimal amount of water is spilled compared to the amount of energy that will be dissipated if Hoover Dam failed. So to summarize the components of electricity, electricity has current and it has voltage. Current is the flow of electrons from positive to negative. It's analogous to the flow of water. Current is expressed in amps, abbreviated with a capital A. Voltage is the difference in potential electrical energy between two sources or reference points. It's analogous to a pressure differential. And voltage is expressed in volts with a capital V, or EMF, or electromotive force, with a capital E. Electricity can also be thought of as occurring in two forms, alternating current and direct current. So alternating current, also known as AC current, is what we typically find in the household outlets. It runs our blenders, it runs our washer and dryer, and it is also found in radio waves. So radio waves and the electrical RF energy within antennas and radio systems are alternating current. So alternating current can be depicted by a sinusoid, which is here, noting that it changes direction going from front to back and back to front. It could also change voltage and go from a positive voltage to a negative voltage and back. So AC is household current, and also found as RF energy in radio waves and antennas. And your household current runs at a frequency between 50 and 60 hertz, or cycles per second. RF energy can obviously vary and can be in the gigahertz, kilohertz, or megahertz range. Another type of electricity is DC, or direct current, and this is what's found in most electronic circuits. This is what powers your radio and powers common handheld devices as well. Direct current does not change amplitude. It does not go from positive to negative, and it does not change direction. So we can just draw a constant line to depict direct current. And the voltage does not change either. So this can be 5 volts. And it does not fluctuate from positive to negative. It just stays a constant positive 5 volts or positive 10 volts or whatever the voltage may be. Okay, let's go over some basic elements of a circuit. So what you can see on the far left portion over here is a battery. So this diagram is called a schematic. That's the electrical engineering term for a diagram of a circuit. So this is the positive end, and this is the negative end, as we can see. And let's just assign this battery to maybe 1.5 volts. And as we reviewed before, the conventional flow of electricity is from positive to negative. But in reality, we know that the electrons actually flow from negative to positive, but we need to abide by the conventional flow of electricity. So these solid lines depict wires that are connected, and they're going to something. This is not the official schematic representation of a light bulb, but it's close enough for the lecture. So this is a light bulb. And with electricity flowing through the system, this light bulb will light and shine. And this is again known as a circuit. And the circuit is a closed circuit, meaning that there are no breaks within the circuit itself. It's continuous. So from the positive end to the negative end through the light bulb, it is a closed circuit. Everything is connected. And by the way, the light bulb can be referred to as one of the components of the circuit, or in this case, it's considered the load of the circuit. So let's say we wanted to change this circuit a little bit. And let's erase a little bit of this wire. So this circuit is no longer connected. So if the circuit is no longer connected, it's referred to as an open circuit as opposed to a closed circuit. So the circuit is open, and therefore no electricity flows and is not connected anymore. Closed circuit, all the wires are connected. An open circuit, there is some type of break within the circuitry that does not allow for electricity to flow. And here you can actually have a switch. And if you shut this, the circuit will be closed. Now, there's something else to consider. So what's a short circuit? So this is the electricity is flowing through the schematic diagram and flowing across the load. If for some reason someone were to put a wire between here and connect it, you're effectively bypassing the load or the light bulb, and this would be a short circuit. You're taking a shortcut around the load, and this would be a short circuit. So given that there are no other loads within the circuit, this would be a very bad idea and be very dangerous, since it would overload the battery and potentially lead to fire or even an explosion. So during this portion of the presentation, we've discovered that this diagram is called a schematic. We've defined what a battery looks like. This is the battery. We've redefined conventional flow of voltage from positive to negative, but in reality, it goes from negative to positive. We've also covered that this light bulb here can be referred to as a component of a circuit. And in this case, it's also referred to as a load. And a closed loop throughout the circuit, one where there are no breaks whatsoever, is called closed. And if there was some type of break in the circuit would be called an open circuit. And to review, this is referred to as a short in a circuit. Components in a circuit can be hooked up in series and parallel. So if we draw a battery here and have our light bulb here and have it hooked up to another light bulb and close the circuit, with the positive end being here and the negative end being here, we can see that these two light bulbs are in series with each other, and this is a series circuit. A parallel circuit is a little bit different. We draw our battery again and make another circuit. And this time we put the light bulb here and connect it up to the battery this way. This is a single component. However, if we extend the circuit and put another light bulb here, we can see that these two are in parallel with each other, and we can put a third light bulb if you'd like to complete the circuit. And these are three components in parallel, as opposed to two components in series on this diagram here. And we'll learn why this is important a little bit later on in the lectures once we get into Ohm's law and a little more on voltages and current flow. Okay, let's get into some basic test equipment. This is something you'll probably use every single day during your electronics career. So this is called a DMM, or digital multimeter. In the old days, we used to have multimeters that had the analog needle on there. I still have one of those, but it's broken. But this is a very useful device. And this is actually the digital multimeter that I have, and from SparkFun, and it works out pretty well. So digital multimeters can measure a variety of things. They can measure current in amps. They can measure voltage. And they can measure resistance in ohms. So we haven't covered the topic of resistance, but we will in the next lecture. But these are the core things that a digital multimeter can measure: current in amps or milliamps, and volts, as well as resistance in ohms. But you have to know where to put the leads. So this comes with two electrodes, or two probes, a black and a red one. If you're measuring so the black one is universally going to go right here in COM. And the red one, you have to determine what you're going to be measuring. If you're going to be measuring things like current on a very low scale, on the order of milliamps, or if you're going to be measuring volts, or if you're going to be measuring resistance, then you would utilize this socket to put your red probe in. However, if you're going to be measuring current on a much larger scale, or larger amounts of current, then you're going to be placing the red probe here instead. So this is for an increased amounts of amperage. And then you can notice that this has various scaling features. So the resistance side is on here, and the volts are here, and you can see that you can also measure AC as well. So you can measure alternating current, and this is volts DC. So you need to have the selector on the appropriate setting. Some digital multimeters are auto-ranging, meaning you don't have to switch from 200 ohms to 20 kilo ohms to 2 mega ohms. It'll just do it for you. But you do have to switch between the different items you want to measure. You need to switch between resistance. You need to switch to amps if you're going to measure current. And you need to switch to the voltmeter portion of it if you're going to be measuring voltage, either AC or DC. So make yourself a checklist. confirm that you have the leads in the appropriate socket, and confirm that you have the proper setting on the ohm meter, and confirm that you have the appropriate range set. And lastly, make sure you are actually making the measurements correctly. So as an example, for current, let's just say you have a battery here. And you want to measure the current going through our famous light bulb that we've been dealing with. There needs to be a break in the circuitry, and you need to put the ammeter, which is depicted as a circle with an A, in series with the circuit. This is how you measure current, in series with the circuit. To measure voltage, you do not put the voltmeter in series. So let's put this here. It's the positive end of the battery. It's hooked up to our light bulb. You're going to use the positive end of the voltmeter. And you're going to put the probe here, and the negative end of the voltmeter, the black wire, you're going to measure here. Okay, so you see you're measuring the voltage with reference to the positive and the negative across the components. It is not in series. It is hooked up in parallel with the component you're going to measure if you're going to measure voltage. And if you're going to measure current, you put the meter in series with the circuit. Okay, everybody, that about wraps it up. So during this presentation, we've reviewed the concept of electricity and its two main components, voltage and current. We've also had an introduction to basic circuits, as well as the circuit design in series and parallel. And we've also introduced some basic test equipment, namely the multimeter or digital multimeter or DMM. And we'll cover some more interesting topics on the next presentation. So have fun, and 73. See you next time.